Okay. I'm probably going to run over time, so I figured I'd just start a minute early. Oh, wait, let me start my screen recording here. So I'm going to be talking about folds and recursion and co-recursion and fun stuff like that in JavaScript. I'll probably be showing lots of code, and you'll probably get really frustrated if you try to read all of it, because I'm just going to keep hitting next, and you're going to be like, stop it. So the point of the talk is to kind of show you alternatives to loops and kind of point out some cool stuff with recursion. And don't get caught up in the details. Just kind of look at it from a high level, and then later on, if you go look into it further, you'll have an intuition and a better understanding. You'll have a head start, basically. So I'm a little hoarse. I did a class yesterday. First horse joke, bam. So try to keep it interesting. Okay, so the agenda is recursion, co-recursion, transducers, monoids, and F-algebras. So much fun, you guys. So let's just do it. So just like there's no crying in baseball, there's no loops in functional programming. And mainly because loops are going to just mutate or do some side effect or whatever. And it's really low level. You have all these little bits and pieces everywhere, and you have to rewrite it every single time from the ground up. We can capture these in functions. So I like to call them SpaghettiOs instead of loops. So let's talk about recursion as an alternative strategy. So we have the sum function, and this is a recursive version of it. And you've got your base case, your action, your recursion. Do you guys show your hands? How many people know about recursion already? All right, great, awesome. So we're just going to go probably pretty fast. So here's reverse. It looks very similar. Look at that. And it's the same stuff. It's got its base, its recursion, its action, something to stop the recursion, something to call the recursion over and over again. And if we look at how it's evaluated, it's just going to keep growing in memory. It's going to say 1 plus the sum of the rest, 1 plus 2 plus the sum of the rest, 1 plus 2 plus 3 plus, and then it finally hits the base case and starts to come back down the stack, and the memory can kind of be released as it folds back down. But don't be worried, don't be scared. ES6, ES 2015 is it's got proper tail calls, or so the optimization for tail calls. And so what does that mean? Well, if we look at our sum, if we actually say first plus the sum of the rest, it has to come back to this particular invocation and add this element to the sum of the rest. And we could rewrite that. Oh, you can get a maximum call stack exceeded and stuff like that. So if we rewrite it way more complex down at the bottom with this helper function called go and an accumulator, we're going to call a function at the end, and there's nothing left to do here, and it can release the memory. So ES6 will give us that, and it'll be great. And we have this reduce function, and that's also tail recursive, except it doesn't really matter how reduce is implemented. This could be with a for loop under the hood. Who cares? Just call reduce. So let's use sum and reverse, in terms of reduce, and the intention's much more clear. We've captured this recursion pattern here that we looked at with sum and reverse and all these other functions that are really useful in this higher order function, and now the intent, the actual style of recursion has been captured. And we could just say it's going to add to the accumulator starting at 0, or we're going to concat onto the accumulator starting at empty list. Much more expressive. We could also define map and filter in terms of this, which is very useful. You guys use map and filter all the time, I'm sure. Most people do. And reduce is very general. It can implement all these other helpful, useful list functions with it. It's actually catamorphism. So reduce is an implementation of a catamorphism. See, catamorpheus? So it's also called a fold. And you can fold left or right. I'm just going to say fold because I don't really care if it's left or right in this talk. And all these really useful functions like all and any and all these things that you would see in Lodash or Ramda or underscore, whatever, that you use on lists all the time can be done in terms of this catamorphism or a reduce. Actually, any loop can be captured with a fold or reduce. I'm going to say fold from now on and stop saying reduce. This is actually kind of a backwards slide because you would think that Superman would be it doesn't matter. So it's because she has a lasso and it's a loop. Okay. So there's other things like an apomorphism, and that's another different recursion scheme. We've got a paramorphism. If those kids in the class, you can capture that with a higher order function as well, and it doesn't matter if it's recursive or it's a loop underneath. But this one's cool. It passes in the rest of the list to your accumulator function, and that'll be useful for things like sorts. But you can still do this with a reduce as well. It just kind of gives you some helping hands here. Anyway, so these extra functions and these recursion schemes can be caught in higher order functions. I like to call them higher order recursion schemes, or horse. Second horse joke. I wasn't going to do that. I thought it'd be too racy. So anyway, so that's recursion in a nutshell. You guys already knew. Co-recursion. This is a little bit more interesting. It's going to get more interesting as it goes along, so bear with me. So this is called an anamorphism. Frozen fans, where my dad's at. So if you've seen Unfold, you can implement this in plenty of different ways. This is just a really simple implementation. You don't have to worry about the code too much here. What we can do with Unfold, though, is we start with 0, which is our seed, and then we return a pair of our value and the next seed. So the next seed here is x plus 1, and our value is the actual character code. And then once we return nil, it stops. So this is basically like the functional equivalent of a while loop. And you can just call unfold, and it'll do cool stuff like that. We've got range we can implement in terms of unfold. So we've got our folds, and we've got our unfolds, and one's generating stuff, one's reducing things down. And we can do this to many other data structures, not just lists or arrays. I'm going to use those two interchangeably. So tree can be folded down or unfolded. And we've got event streams that can fold with an accumulator. We've got objects, infinitely many data structures. You can just fold it down. There's an intuition about it. We say we have this data structure and we want to kind of reduce it into a value with an accumulator. So there's something important here. There's some kind of theory and something really general that if we can understand and get at, we can define this for many different data types. And we can find all those useful list functions. Those ones that any, all, sum, find, sort, like these things are really, really useful. So here we go. We've got a linked list that we're going to use for ourselves. So we can kind of investigate this mystery. Do you guys know linked lists? All right. It's basically the first element's the head and the rest is the tail. So cons 3 and its second property is the rest of the list, all the way down to nil. And we could represent that with a JavaScript object here. I'm going to, by convention, do this gross thing of calling underscore cons as my object, but then a non-underscore cons, so I just don't forget to write new. And nil is just a singleton, so I don't have to do that. But for the rest of the talk, I'll be doing underscore for things that are actual objects, and the rest is just a public constructor. So yeah, here's our cons linked list. And we can do the same thing with trees. Don't worry about it, it's the tree definition. So that's co-recursion. And I define those extra helpers so we could look at things throughout. So transducers, are you guys excited? Do you guys know what transducers are? All right. Cool, let's look at those for a second. I'm not going to go too deep into it. I just want to kind of explain the idea behind them. So if you have map and you're doing a reduce, this is kind of just like a general reduction here where we have a few things going on. We have an iterator, so we're doing iteration, we're doing accumulation, and we're doing transformation. So as you walk your list, you've got your input list, and then you've got your output list doing accumulation. There could be two different types, right? I could start with a list and end with a number or whatever. So our accumulator and our iterator thing have two different types sometimes. We transform everything. So I'm going to make some terminology here. This first argument to reduce, I'm going to call that a reducing function or a reducer. Let's just call it a reducer, okay? So this first argument to reduce is called a reducer. It takes an ACK and an X, and it just returns a new accumulator. So what if we kind of pull out the reducing function, the first argument to reduce, and we just return it by calling mapper. So I call mapper, and it just gives me the first argument to reduce, and there we go. Why would we do that? Well, let's make it a little bit more general. Since this reducing function is also dependent on concat, let's pass in concat there. So we're giving mapper a function to map and its way to accumulate, right? It's concat. And we can do the same thing with filter. Here's our filterer. So basically all these functions are doing is returning the first argument to reduce, a reducing function, a reducer. And that's the reducing function. But look at this signature here. The concat function has the same arguments and does the same thing as our reducing function. It takes an accumulator and an element and returns a new accumulator. So that means our concat function, our accumulating function, is a reducing function as well. We can actually just pass concat directly to reduce, and I'll just copy the list. So we can pass other reducing functions to other reducing functions all the way down, and it's like reducing inception. So you basically, when is that inception thing going to get played out? So you've got concat, and that passes that into mapper, and that makes a reducing function, and that turns into the concat pass to filter and makes a reducing function. All these things return reducing functions. That's called function composition. And we can actually make a kind of a pipeline of transformations. And mapper and filter here are called our transducers. So transducers are just the mapper, just the filterer part. But the interesting thing here is that the reduction itself is in one loop. There's no first you map over the whole thing, then you filter the whole thing. It's just we're going to make this this transformation pipeline that's totally ignorant of its input and its output, and we're just going to give it to the reduce so it does it once, and it will both filter and map. So that's really cool. It does this kind of stream fusion for us. We kind of do it manually as we build it up. And as a bonus, we have our list here, and we have an iterator protocol that we can program against in ES6. So I'm using fat arrows here because why not? I'm talking about ES6 anyway. But so we can iterate over this list, and we don't need to keep its shape. So we can actually use the iterator protocol to implement this reduce. But this part is a little bit trickier. We don't have a protocol here for accumulation. So we have to know that we want to start an empty list, and we have to know how to build it up, how to accumulate them together. Same thing with our linked list here that we defined. We can make it an iterator, that's all good. But what about this nil and append? Like, we have to have them publicly available to kind of construct this computation, and we have to know like where to start and how that works. And same thing with our tree here. So we've got kind of our iteration just done, iterator protocol, cool. We've got transformation, just grand slam, out of the park. Like, we can build up composable, generic transformations that work on any data type because they don't care about their input and they don't care about their output. We're actually feeding that stuff in. And then the accumulation, not so much. There's no real protocol to work on, and I have to know stuff about what I'm trying to build up, and I have to have access to those functions. So I just lied. There is actually a protocol for building things up. It's called a monoid. So let's talk about them for a minute. So let's see here. Concat actually has some properties to it. So we just saw concat in the empty list. And it turns out if you concat an empty list to the left or right of any list, you'll just get that list back. Right? It's just like a neutral thing that doesn't do anything. So it's a great place to start. And then it's also associative. So you can concat a list with another list and concat that with a list, or you can flip it around. You'll always end up with the same result. So in Fantasyland JS, there's actually a specification for this. So it's saying anything is a monoid if it has its concat and its empty method, and it abides by these laws or this contract, or however you want to say it. Let's do that. Let's make a monoid. So it turns out array was already a monoid with concat and empty array. But let's make a few other ones. So here we have sum. And we're going to do something wacky. We're going to make a sum type, like an object. We've got that underscore private thing and then my public constructor. And it's just got one property called val. And then we basically put the first arguments to reduce on the type itself. So the first argument to reduce is going to add two things together. That's what our concat's doing. It's saying, I've got a sum, so I'm going to add it to another sum. We're going to add their vowels together. And then we start with an empty sum with a 0 as its first argument. So these two kind of correspond to each other. The concat and empty are just the first two arguments to reduce. And if we have that, Well, we can make a reduce that doesn't care about its first function or its seed argument, or its first accumulator. We could just call it directly with a list of this type, and it can figure out what those are. So folding down a list of sums will give me a sum of 10. Now, the first time I saw this, I was like, why the hell would anybody do that? It's so weird. I would rather work with functions. What am I doing, like making this sum type that's only good for this? But it's actually really useful. We'll look at that why in like 2 or 3 slides from here, so just hang tight. But so we've got a fold that will just fold this list down into one sum. And this should be relatively clear what's happening, even though I'm just blasting through slides. So sorry if you get lost in the code. So we can do the same thing with product. Product can be combined with multiplication and start with 1. We can fold that down. We can do the same thing with max and min. Just always keep the highest and start with negative infinity, which is an actual JavaScript value, which is so cool. That should be my new avatar. I want it's negative infinity. And we've got all and any. So this works for Booleans and stuff too. It's so all just says, hey, everything in the list. And guess what? Don't these look a lot like those really useful list functions that we listed at the beginning? All, any, sum, product, max, min. Yeah, these are really useful functions just kind of put into a type. You remember we were able to reduce things and make things in terms of reduce. Well, now we're putting those arguments on the type themselves. And we'll see the benefit. So you can make all these functions with these things. We'll see the benefit of that here in a second. Also, I'm iterating over a list here, which is, we get that iterator protocol, so that's cool. We can iterate over other data types. So we can make this little fold map function. This is a really simplified version, and it depends on map, so don't worry about it too much. There's a really complex one that uses the iterator. But if you look down at the bottom, we've got sum, max, any, and all it's doing is saying, hey, take your list of something, make them all sums, and then fold it down and give me the value. Or put your list of anything, make them all maxes, and fold it down and give me the value. Any, all, that's how you can basically define these functions. And we can make them work on anything that's an iterator. So that's pretty great. So we've got our tree sum, our tree product, and our cons any, and our cons all. And it's also, because of that associativity, we can do it in parallel. So that's pretty great. To be fair, you're not going to get much of a win if you try to do parallelism in JavaScript. You're going to have to spend more time chunking an array and running down the list. But it's often useful to know that property just in case you do want to try that. So we've got our iteration done, and our transformation, not so much. Because these things are already built in. We're not actually transforming anything. We're just saying, hey, make my sim, make my product. Like, I'm not running functions on values. But the accumulation is what this is all about. We're killing it there. So this is kind of different from transducers. And in fact, there are monoidal transducers that you can use. I'm not going to talk about them today, but you can kind of combine the two. So if you look at this type, we've got this array of sums, and it's going to give me a sum. And or a list of products, a list of max or mins, and it basically takes it down a type. Like we've got some type of another type, and it gives me that other type. That's kind of the idea behind folding, right? If I reduce a list of things, I'll get one value. And this f of a, this some type of a to a, even though the type is a list of another type, that's called an algebra. So let's look at F-algebras. And no, not that F. A lot of people are like, F-algebra. So catamorphisms, we can actually, there's a lot of ways to skin the catamorphism. And this is another way to do it. So we've got this two things to notice here. We're depending on map here, and we actually are depending on map here. We can't use the iterator protocol. And it's going to recursively call itself. This is an entail position because I wanted it to be simple and readable, but you can totally do it. So this will map over everything and recall itself over and over again until it hits the fixed point of our functor. What? So the fixed point of a functor is anything with the map method and behaves correctly. And you can look that up. And the fixed point is the thing that returns itself. So it has a map method, and whatever returns itself is called the fixed point. So if we, you guys know the Y Combinator. This is kind of like the type level version of that. So map, nil.map, it's a functor, and it returns itself. Awesome. That's the fixed point of the functor. Kahn's prototype map, that will actually pass F into its children, or it will give its children to F, its tail. So this is not the intuition you might have normally when you're looking at a map. You would think, I have a linked list, and I want to run a function on every element. That's what I think of when I want to map. I want to map over every element. But here I'm not calling F with the element. I'm calling F with the tail. It's the children that we're after here. It's like the child snatcher. Sorry, Chitty Chitty Bang Bang fans. Just to be aware of, if you're going to do this, you need to define a different kind of map. So we look at our sum function here. Up here, it's called an algebra. There's an algebra. Because it's going to take our x, which is our entire Kahn's linked list thing, and it's going to return us a value out. So it takes it out of its type. And then we've got our list here. And if we give sum, our algebra, to kata, it will actually fold our structure down. So that's a wacky thing to do. Let's look at how this actually works, though. So the first time x comes through, it's nil. So it's starting bottom up. And the next time it comes through, you've got cons 4 onto 0. And that's, if you're paying attention, that 0 shouldn't be a 0. It should be the tail of the rest of the list. And every time it's coming through, it's actually already folded by that point. So I'm not actually working with any recursion. I'm just working with one level, and all its children have already been folded by that point. So I don't have to worry about anything recursive. I just pass it to kata, and I say, do it. And here I'm working with a list of 4 and 0, then 4 and 3, or 3 and 4, and then 2 and 7. It's pretty cool. So it's summing that bottom up. So we can make map in terms of this catamorphism. It's pretty cool. It's like our F-algebra version of map on our linked list. And we can do the same stuff with trees. Here a map, empty is a fixed point, and we're passing our children into F, and we can sum this down. And look what's happening here. I don't want you to cringe at the case statement, but it's the best I can do for pattern matching here. But the idea is that we've kind of pushed our data-specific stuff to this inline algebra here we're passing to kata. So this is the part that needs to know about our tree. And the catamorphism takes care of all the recursion for us. It just calls itself in map. So let's talk about an anamorphism in this way. So we've got again, we're depending on map, and we're recursively calling ourselves. And this is called a co-algebra, this array to list, which is a co-scary word. Anyway, so this array to list is basically going to take a value that's not in a linked list and then put it in one. That's why we call it a co-algebra. It takes our A to our F of A. And we've passed that co-algebra to our anamorphism, and it'll make us a linked list, which is pretty cool. We've got this make alphabet that, just like we saw before, we can do this kind of unfold. But this is basically working with our linked list type, and we're passing in algebras to this recursive thing that just takes care of it for us. We don't have to worry about any recursion, or co-recursion in this case. We can do the same thing with range. Cool. So there's F-algebras. We've got our iteration and our transformation and our accumulation. We kind of dropped the ball on the iteration because we have to define our own map that doesn't work like an iterator. It's passing all the children in at once. But the other things are cool. Transformation, we're just doing whatever there, so we can do that, and accumulation works great. But this is where it gets interesting. So it's kind of like building up to this part in the whole talk. So if you're going to pay attention to anything, pay attention to this. Programs are actual data structures that can be folded down into a value. It's called interpreting the program. So you can build up a structure of instructions, and then you can interpret that via catamorphism. So, sorry, yeah, you're welcome. So here we've got to add 2 and 3 together, we'll get 5, and then we'll multiply that by 4. So we have to wrap these things at the type level. These are unevaluated, pure data structures representing our program that we're going to fold down. And we could do this, this object definition, same as always. And then we're going to pass the map, the children into map. And this is where it gets interesting. We have our interpreter that takes our structure and just runs these functions. If you hit multiply, multiply them. If you hit add, add them. Otherwise, just get the value out of a constant. And our program gets interpreted, and we do indeed get 20 out. I have the gist if you don't believe me. So you can download and play with that. But this is really cool. This means we can make programs that are entirely pure, and they're just instruction sets that we can kind of build up dynamically and pass around and compose and combine. And we can write interpreters, one for maybe a test, and one for, when we're in the browser, one on the server. It's really interesting stuff here, and we could send them over the wire and whatever. So we can do this again with like concat and replace and input, just to illustrate. We pass our children in. And this interpreter will turn hello world into mellow world, which is pretty cool. And so it runs right to left, and it'll fold down that data structure. But we can also do this one. It's a different interpreter that actually describes what's happening. It's saying concatenating the world after replacing H with M on hello. So basically these interpreters are when things actually happen, and everything else is pure. Think about that. If you're doing API calls or writing files or deleting things, and all that's really hard to work with and test, and you can actually just generate your instruction set and pass that around and work with your little algebra that'll interpret it down. And if you've heard about free monads, this is like half of it, and the other half is the pure, but you can do coroutines and stuff with it. So this is like almost a free monad. It's a very, very important design strategy and architecture pattern in functional programming, because it basically makes everything in your application pure, and you don't have to worry about side effects at all, and then you can interpret it down, and you can make little sub-algebras throughout your application, which is really neat. So that was my F-algebras and my monoids and all that stuff. So next time you're sitting down to write a loop, and you're like, should I write another for loop? Stop and think, like, how long are these for loops going to be around? They don't really have the composability, and they're not being captured, and this and that. So there's my talk. Thanks. I started a minute earlier, so I guess I have a minute or two for questions if anybody wants to ask a question. I won't make you feel stupid, I promise. Okay. Oh, what's up? Yeah. That's right. That's kind of the idea of an algebra. You take your f of a to an a. So it's like a fold. You just write down out of the data structure. And that's, if you look at reduce, same signature. Pretty cool stuff. But that goes to A to B, and I think algebras take A to A. So that's something else. Anyway, anybody else? You can go to this GitHub repo and play with this stuff. Oh, there's also bifunctors and stuff in there that I didn't really get to talk about, because when I practiced it at home, I kept going 10 minutes over. So I just cut it all out. But there's stuff called like bifunctors, and they've got things. There's bimap. Anyway, I'm not going to waste your time. All right, thank you guys.